This is R. Raghupathi, working as Assistant Professor in Civil Engineering, Government College of Engineering, Bodi Naiknur. I am hereby presenting a video lecture on C8301, Strength of Materials 1. You see that this is unit number 1 and the topic is stress, strain and deformation of solids, and there are a lot of topics to be covered under this unit 1, in which I am going to give in this video lecture only two topics. One is simple stresses and strains, another one is stress strain diagram. Yes, here first let us say strength. What is strength? The ability of a part or element of a structure to resist failure. Yes, so up to failure, what the magnitude of load that can carry, so that is called as strength. The failure is nothing but we can fix the criteria of failure. Sometimes a material can carry only up to elastic state, so once it reaches the load, that elastic limit, the material may fail. Like that we can fix the failure criteria for that particular material. So for example, if we have glass cannot go beyond the elastic limit. Yes, so like that, so depends on the material we can fix the failure criteria. Some other material we can go up to ultimate state or breaking state. Like steel we can go up to ultimate or breaking state. So the failure can be fixed at that point or at that level, either ultimate or breaking level. The next, stiffness. Stiffness is the ability to resist deformation. Yes, so if a material or if a member is said to be more stiff, that means it can resist more deformation. Next, assumptions made in strength calculation. The material of a body has solid continuous structure. Of course, this is the basic requirement of a material which is to be used for engineering purpose. So very important assumption. The material of a body has solid continuous structure. Next, the material is homogeneous and isotropic. What is homogeneous? A body is said to be homogeneous if it has identical properties in identical direction, which means that material should have uniform composition throughout the section and it should have uniform properties in all directions. Next, isotropic. A material said to be isotropic if at any point it identical elastic properties in all directions. Let us take a point in a isotropic material. So that point, in that point, it has uniform elastic properties in all directions. Next point C, there are no internal force in a body prior to loading. Yes, the internal resistance is developed only after the application of external load. So that point is telling in assumption C. Assumption D, principle of superposition is valid. Yes, any linear system, this principle superposition should be valid. Then Sine-Venant principle is also valid. That means the stresses subjected in a body along its length are uniform. So that point is saying in assumption G. So these all things will be discussed in further topics. Next is simple stresses and strains. First, stress. The internal resistance offered by a body against a deformation is called stress. Yes, suppose if a member is being loaded, which means it will not fail, there will be internal resistance developed. So this internal resistance is said to be in terms of stress. So this stress cannot be physically measured. So it is mathematically represented. Stress sigma is equal to force per unit area. So if you apply any force P at an cross-sectional area of member, therefore stress can be calculated by knowing that magnitude of force divided by cross-sectional area of that particular member is called as stress, can be taken. Next, types of stresses. First one is normal or direct stresses. What is normal or direct stresses? The stress due to an axial force. It may be either direct tensile or compressive stress. Suppose a member which is loaded uniformly along the axis of the member. That is very important. Suppose let us take this member or this bar which is applied axial tensile force capital T, and therefore the axial tensile stress sigma or normal stress sigma is equal to T divided by A. Like that, there is another member which is carrying axial compressive force because this load is applied along the axis of the member, and this is the axis and this is length axis. So that this is the length of the dimension, this may be thickness of the dimension, there is another dimension breadth is available. Yes, sigma is equal to, now this axial compressive stress sigma is equal to the axial compressive force C divided by the cross sectional area of the bar. So like that we can calculate the normal or direct stresses. It is also called as axial stresses. Next, shear stress. Shear stress is this axial stress is calculated perpendicular to the plane. That's why it is normal stress. Suppose there is a plane B and T, so this normal force is acting perpendicular to that plane, whereas this shear stress is parallel to that plane, or it is acting tangentially on the surface or plane. This plane surface, it is acting tangentially on this plane surface. That's why it is called as tangential stress. So the stress is developed due to a tangential force acting on the body F, that is called as shear stress. So the shear stress can be calculated, tau is equal to the shear force F divided by that sheared area. That sheared, this plane area is giving the shear stress. Next, bending stress. The bending stress is nothing but a stress is developed in a bending member due to applied this kind of transverse loads W1, W2, W3 or any other system of transverse loads. The bending stress is developed at all the section of the this kind of beam. So if we take a cross section of this beam like this rectangular section, and this section consists of infinity fibers. So these fibers are having different stresses. So this is called as neutral axis. Above neutral axis, the section of this beam is subjected by bending in compressive stresses. All the fibers on above the neutral axis are subjected by bending in compressive stresses, and all the fibers below the neutral axis are subjected by bending in tensile stresses. Yes, these case may vary. Suppose in some cases the top fibers, all the top fibers are subjected by tensile stress, and all other bottom fibers are subjected by bending in compressive stresses. So as far as the bending member is concerned, every section is subjected by two nature of stresses, bending in compressive as well as bending in tensile stresses. So these bending stress can be calculated using the relation sigma b is equal to m by z, where m is equal to bending moment at that section and z is equal to section modulus. Next, stress due to torsion. So torsion is nothing but a twisting moment. Twisting moment is applied to some member. Therefore, there will be torsional shear stress induced. Okay, so this is nothing but torsional shear stress. So these are all the different types of stresses. So far we have seen different types of stresses. The first one is normal or direct stress, the second one is shear stress, third one is bending stress, and fourth one is stress due to torsion. Torsion or twisting moment which is given to the member, and therefore the shear stresses are developed at that section of the members. So these all stresses will be dealt in detail in coming units. Next, now we just see the introduction part only. Then next, strain. How can we find the strains? What are the types of strains? Let us see one by one. The first one is longitudinal strain. or it is called as direct strain, or it is called as linear strain. So this longitudinal, direct or linear strain can be defined as the deformation per unit length caused by normal force in its direction. Suppose this is the axis of this member. So if you apply the force along this axis of the member, and therefore this member is deformed along this axis, let it be delta L. So we apply as far as in this case there is a bar which is fixed at one end, and another end there is a pull P applied. So there will be an elongation del L of the span of the bar L. Yes. Then how can you find this strain? Strain is nothing but the deformation per unit, and therefore it can be expressed as the linear strain is equal to change in length divided by original length, that is epsilon is equal to del L by L. So this is the mathematical expression for finding this strain. So strain can visually, we can feel visually. Suppose a member or a material is loaded, once it is strained, so that can be physically viewed. We can see that one, we can feel, and that observation can be taken. What is the deformation takes place? So that thing should be taken, that is del L. And what is the original span? So del L divided by original span, which gives the strain, that is epsilon. So next let us see the Hooke's law. Hooke's law, what is Hooke's law? Stress is directly proportional to strain within the elastic limit, strictly speaking up to proportionality. So sigma is directly proportional to epsilon as per this Hooke's law. In order to eliminate this proportionality, we introduce a constant E. Therefore sigma is equal to E into epsilon, that is stress is equal to E into strain. What is E? E is nothing but the Young's modulus of the material, and the above is valid for uniaxial force only. Yes, this kind of equation can be used only for uniaxial forces. Uniaxial forces means, that is, we apply the force only one direction. We apply the force only one direction. You see that? So this is one direction force we have applied, because it has some other phases also, that side phase, this side phase, another side phase, but we apply the force only one direction, that is only one direction force, that is called as uniaxial direction force. Now you see here, and therefore now sigma is equal to E into epsilon, therefore E is equal to sigma by epsilon, then epsilon is equal to sigma by E, and we know that the sigma can be written as P by A, force by area, divided by E. So epsilon is equal to P by AE, and we also know that the epsilon is equal to del L by L, that is change in length divided by original length, which is equal to P by AE. Therefore from which we can find del L is equal to PL divided by AE. What is del L? Which is nothing but axial deformation. Suppose here, if a bar is subjected by an axial deformation, this del L, so this del L can be calculated using the relation PL divided by AE, where P is equal to uniaxial force acting on the bar, L is equal to length of the bar, A is equal to cross sectional area of the bar, and E is equal to Young's modulus of the material. Then so this is axial strain. So far we have discussed about the axial strain or yes. Then next, shear strain. Shear strain is pi. In case of tangential force, change in angle measured in radians is called shear strain. So here we take a plane which is subjected by shear, and because of the shear the object is distorted. So this pi is nothing but distorted angle. So this measurement of this distorted angle in radians is said to be shear strain, that is pi is equal to B dash divided by AB, that is called as shear strain. Yes. Next, volumetric strain. So this is another type of strain. The volumetric strain epsilon V is equal to the ratio of change in volume to the original volume. It is also known as dilation. So how can we define the volumetric strain? It is nothing but the ratio between the change in volume to the original volume. So we have already seen the linear strain or longitudinal strain, which can be defined as the ratio of change in length divided by original length. So that is called as linear strain. Here it is volumetric strain. Therefore, it is change in volume, ratio between the change in volume and its original volume. So this, how can we find the change in volume? So that one depends on different types of material. Yes, and we have to find the change in volume in each direction, from which by sum of the strain in each direction, which gives the total change in volume, that is epsilon V. Next, problem solved. We just try a small problem. A rod 150 centimeter long and diameter 2 centimeter is subjected to an axial pull 20 kilonewton. If the modulus of elasticity of the material of the rod is 2 into 10 power 5 Newton per mm square. So what is the modulus of elasticity of the material? That is nothing but Young's modulus, E. Yes, that is nothing but an elastic constant. Here, determine the stress, the strain and the elongation of the rod. So here area of the rod A can be calculated initially, since it has a diameter of 2 centimeter, and therefore pi by 4 into 20 squared, that is we substitute in mm, which is equal to 314.15 mm square. Next, the stress sigma is equal to P by, as we know that it is an axial pull, therefore we are finding axial stress or direct stress. The formula is sigma is equal to P by A, and the axial pull 20 kilonewton, it is converted into Newton, therefore 2000 Newton divided by area in mm square. Finally we have the stress 63.662 Newton per mm square. Next, strain epsilon is equal to, we have different formula. One is the simple formula is del L by L, but we don't know del L, it is not directly given, it is going to find, and therefore we are having some another formula. So that is what is strain as per the, if we know the Young's modulus equal to stress by strain, and therefore from which strain is equal to stress divided by Young's modulus. We have already calculated stress, and the Young's modulus of the material is given, that is modulus of elasticity of the material 2 into 10 power 5, and therefore strain is equal to this stress divided by Young's modulus 0.000318, that is strain value. Next, by knowing this strain, and we can find the del L, which is equal to, that is change in length or elongation, which is equal to strain into original length, because strain is equal to change in length divided by original length, from which we can find the change in deformation is 0.0477 centimeter. Yes, next let us see the stress strain diagram. So this diagram is plotted by doing the tension test on mild steel with the use of UTM. So normally it is being done in the strength of material laboratory with the use of UTM, universal testing machine. So first let us see the for ductile material. For that we took the mild steel. So we just took the mild steel and fixed in the UTM, and we have done the that is tensile test on mild steel. So that done in the strength of material laboratory. So and we took the different observations at a different state of load, so from which we can plot this kind of graph, this kind of curve. So this is nothing but stress strain curve on mild steel. So here we have crossed a lot of range of loads as well as stresses while increasing the load. So first here 0 to A, there is a straight line range, that is linear range, that is origin O to A, OA. So up to A it is called as at A it is called as proportional limit. Then at B elastic limit. So there is a small difference between a proportional limit and a elastic limit. Okay, proportional limit and elastic limit. So the first point is proportional limit, next is elastic limit, then C is upper yield point and D is lower yield point, and DE is called as yielding or plastic zone, and EF is strain hardening zone, then F is ultimate stress or ultimate point, whereas FG is necking zone, and G is rupture stress or breaking stress, and EG dash is true stress strain curve corresponding to EG. Yes, actually you see that. So let us see one by one. So here we are getting two types of yield points for this mild steel. That is, upper yield point is unreliable and it varies with the shape of specimen, rate of loading, and not considered as yield stress. So here we have to find the different stresses corresponding different loads. You see that if I want to know the elastic stress, the elastic stress means here O to A, the range of stresses in between O to B all are elastic stresses. Okay, the range of stresses within O to B, this O to B are all elastic stresses. So like that we can calculate the different elastic stresses corresponding different loads up to this point B. Okay, then I want to know the stress exactly at the proportional limit, so from which we just note the stress at the point A, that is proportional stress at the proportionality limit. Then I want to know the stress at the exactly elastic limit, so that is nothing but stress at the point B, corresponding at point B, so that is nothing but elastic limit stress. Okay, then finally further I increase, what happen, I get some other yield load at C, that is called as upper yield load, and its corresponding stress upper yield stress. Then the stress gets reduced up to D, so that is nothing but lower yield point. Okay, lower yield point. So when compared to this upper and lower yield point is most reliable, and therefore it is being considered as yield stress. Okay, this point D at is called as yield stress on mild steel. Then DE is yielding or plastic zone. Yes, then nominal stress strain curve. Next let us see the nominal stress strain curve. The curve based on original area of cross section of specimen while calculating various stresses. So what is original area of cross section? That is initial area of cross section. You see that if we see this stress strain curve here from O to A, B, C, D, E up to F, we are calculating the stresses based on the original cross sectional area of the bar. That is initial cross sectional area of the bar. Suppose if we have if we want to know the yield stress, then we just measure the yield load divided by the area of the bar, that is cross sectional area of the bar, that rod which is measured at initially. So we use that dia. Up to F it can be same, whereas F to G, here the necking zone formed. So what is necking zone? What do you mean by necking zone? Which means after F the dia of the bar is adversely affected, that is the dia of the bar gets reduced for further increment of load, that is called as necking zone. But we are using further the same initial dia of the bar for calculation of area to plot this stress, and therefore this corresponding curve, once the curve is plotted for all the range of stresses by taking the initial or original area of the bar, that is called as normal stress strain curve. Yes, nominal stress strain curve. Whereas there is another type of stress strain curve, true stress strain curve, which is curved based on actual area of specimen. At the same time, the force is varied to calculate the stresses. So here the true stress curve means you see the FG days. This is nothing but the curve corresponding to the necking area being considered. So here the original area of the rod is considered hereafter. That's why the curve is getting like this. So this is called as O, A, B, C, D, E, F, G days are called as true stress strain curve, whereas O, A, B, C, D, E, F, G is called as nominal stress strain curve. The next, gauge distance. So gauge distance is nothing but we just mark any 2 points on the bar or on the rod while doing the tension test on mild steel or torsional, whatever may be. We just mark any 2 points within that length of the bar, and this is for taking the deformation purpose. So within this gauge distance, the deformation is observed at different loads. So that distance between these 2 points arbitrarily fixed, that is called as gauge distance. Next, elastic material. What is elastic material? Material which regain its original size and shape on removal of stress is said to be elastic material. So when you see this curve, so this green range, that is O to A or O to B or O to B, these are all the elastic range. So once if we remove the load up to B, what happen? The strain becomes 0. There will not be any yielding, or there will not be any permanent strain. So because these are all within the elastic limit, so that is called as elastic stress. Then ductile material. A material which can undergo considerable deformation without rupture is said to be ductile material. The major portion of the deformation is plastic. Suppose let us take this diagram. You see that it is a typical stress strain curve of ductile material, because it is having wide range of the stress strain curve beyond the elastic limit. So therefore it is having large deformation. So this is the state of breaking. This point is breaking, and therefore before breaking it is subjecting lot of deformation. So that is nothing but ductile material. So after elastic range, the material is having wide range of deformation, that is called as ductile material. Next, set or permanent set, which means the deformation on strain remaining in a body after removal of stress is known as permanent set. Yes, once the range of load or stress once the range of stress or load is going beyond the elastic range, what happened there and after that if you remove the load, what happened? There will be a residual strain or residual deformation. So that is called as permanent set or set. Next, elastic limit, the greatest stress that material can take without permanent set after removal of stress. Yes, you see that. So this is the greatest stress of B. So let us take the point B. This is the greatest stress at elastic limit, because so up to which if you remove the load, the strain becomes 0. So beyond B, what happened? If you remove the load, the strain may comes down and stop here. Okay, there will be some permanent set. Okay, then next, proportionality limit, the greatest that a material can take without deviation from straight line relation between stress and strain. Yes, so this is proportionality limit, straight line portion, O to A. So A is proportionality limit, this is linear portion. Okay. Then strain hardening. Strain hardening, the increase in strength after plastic zone due to rearrangement of molecules in the material. So this zone is called as E to F is strain hardening zone. So which means this is yielding zone. So once the point D is said to be a yield stress of that steel, so this is nothing but yielding zone. So once it attains yielding zone, you just listen, there will not be any increment of stress, but strain only increases, permanently strain only increases. So this is called as yielding zone. What is yielding zone? Yielding zone is nothing but the without increment of stress, the strain increases. So at D there is constant stress, but strain rapidly increases. This is called as yielding zone. So once the point E reaches, what happen? Further the stress increases. That is called as strain hardening. Strain hardening as well as strain also increases. This is called as strain hardening. This is due to the molecular rearrangement. That is called as strain hardening. So once it reaches to F, that is called as ultimate state. So after that the curve comes down. The curve comes down. This is nominal curve. So once if you draw the nominal curve, the curve comes down. Otherwise if you draw the true stress strain curve, the curves further goes up to breaking state. So at G the material fails or breaks. Yes. So far we have discussed the different range of stresses and different range of loads and different range of points on the ductile material, that is stress strain curve on ductile material. So next let us see the stress strain curve for tar steel. This it is also one of the type of steel, tar steel, which is being used for engineering purpose, construction, some other purpose also. Stress strain curve for tar steel. So tar steel and aluminum do not have any specific yield point and yet undergoes large strain after the proportional limit is exceeded. So tar steel is also one of the ductile material and therefore it has wide range of deformation after the elastic limit. And here it is not easy to fix the yielding point as mild steel because it is tar steel, and therefore how can we fix this one? We just draw a parallel line against the straight line portion of stress strain curve, okay, and which cuts a point A on the stress strain curve, that is nothing but the yield stress. So at which point is to be chosen? So we have to choose the 0.2% strain in order to draw the offset line parallel to stress. So for that we choose the 0.2% strain. Okay, so therefore the stress corresponding to the 0.2% strain is called as yield stress as far as this tar steel is concerned. So a line is drawn parallel to the linear stress part of the curve, but is offset by standard amount of strain 0.002 or 0.2%. Okay. Next, stress strain curve for brittle materials. So this is nothing but the typical curve of stress strain curve of a brittle material. So you see that if a typical brittle material is not having wide range of curve beyond the elastic limit, it has very small range of curve and there will be a small deformation. In case of ductile material, it is having wide range of deformation, it is subjected by large deformation before it breaks, but in this brittle material it is having very small deformation at its breaking state. So this is the major difference. And we can say some brittle materials, concrete, stone, cast iron, glass, these are all the brittle materials. Okay, sometimes high carbon steel may behave a brittle since they have more yield stress, but fracture occurs with a little bit elongation. The stress strain curve for glass in tension is essentially a straight line with failure occurring before any yielding takes place. Yes, glass is having only the straight line part. Then last one is stress strain curve for an ideal plastic material, a material which can undergo permanent deformation without rupture. You see that there is no straight line, linear straight line portion for an ideal plastic material, and from zero stress to there is no a constant. Once it attains a constant plastic stress, if we apply a constant plastic stress to the plastic material, and we get the constant increment of or not increment, a constant plastic strain that we can obtain. Yes, the following are the results of tension steel. Let us see a problem. The following are the results of a tension test on mild steel rod. Diameter of the rod D is equal to 16 mm. Gauge length for deformation measurement L is equal to 50 mm. Load at the proportional limit, that is PP, load at proportional limit, which is equal to 48.5 kilonewton. Extension at the proportional limit del L is equal to 0.05 mm. Load at yield point Py is equal to 50.3 kilonewton. Ultimate load P is equal to 90 kilonewton. Final length between gauge length L1 is equal to 64 mm. Diameter of the neck at fracture D1 is equal to 13.7. This is the neck zone. The diameter of the bar at neck zone 13.7 mm, but initial dia is 16 mm. So the diameter of the bar reduced at necking zone. Determine the Young's modulus, elastic limit, Young's modulus at elastic limit, yield stress, ultimate stress, then percentage of elongation and percentage reduction in area. So area of cross section, first let us find the cross section area of the bar, then stress at proportional limit. We know the load at proportional limit divided by actual area or initial area bar, we obtain 241.2 Newton per mm squared. Strain at proportional limit is we know that change in length, that is change in deformation, is given at proportional limit, and we know the original length of bar, and therefore we get the strain at a proportionality limit. Then Young's modulus E can be determined by knowing stress by strain. We know the stress at a proportionality limit, and we know the strain at a proportionality limit. So these are all coming within the straight line linear portion, and therefore E can be found using this relation, that is stress by strain. Yes, it comes 2.41 into 10 power 5 Newton per mm square. Then yield stress equal to, we know yield load, then actual area of the cross section, therefore this one, and then ultimate stress, also actual area of ultimate load divided by actual area of cross section. Then percentage elongation can be calculated using the relation final length minus initial length divided by initial length into 100. So it is given 64 is the final length of the bar, it is given, and initial length of the bar is 50 divided by initial length 50 into 100, which is equal to 28%. Then percentage reduction in area, again initial area minus final area divided by initial area into 100. So the dia of the initial bar we know, and this is the area at the necking zone, dia of the necking zone, and therefore corresponding area is final area. So finally we get the percentage reduction area. That's all.